surface, and here is a ball, and it connected to a spring. So when it put forward to here and then release, it will move back and forth like this. Will move back and forth like this. So we call this an oscillator. And you can see at here, the position O, we call it equilibrium position, because at this position, the net force on this ball should be zero. And if at this position, we choose this position to be the origin, and we can draw an x-axis to this direction, and here's the origin. So the position of this ball can be described by its coordinate x. So then we can find that the force, the net force on this ball satisfies this equation. F is equal to minus kx. X is the displacement relative to the equilibrium. And K is called spring constant, which is a constant if for spring, which is a constant for spring. And here F, we call it restoring force. It's the net force on this ball. And it's the force due to this spring. So why we call it as restoring force? So because this force always bring the ball back to its equilibrium. So you can see when it go far away from this position, it will pull it back. It will pull it back. You can see this force, direction of the force, always point to the equilibrium. It seems that this force always tends to make the ball go back to the equilibrium. So if there's no restoring force, the ball will not go back to its equilibrium. It will not move back and forth. So this restoring force is the reason why it moves back and forth. So here is the minus sign. It means it's always in the opposite direction of displacement. The magnitude. So you can see the greatest distance from the equilibrium point is called the amplitude. You can see the distance. This distance is the magnitude. The farthest position it can go is the amplitude. And the period of this oscillation is the time that required for a complete cycle. For a complete cycle, time required for a complete cycle is called period. And also frequency, the number of complete cycles per second. And the relation between frequency and period, F is equal to 1/T. That's a relation between period and frequency. So maybe this oscillator is the simplest model of the oscillation, but this not the only model of the oscillation. So like if you hung a ball by a wire, that's just like this. So this, if the wire is long enough, this is called a pendulum. And if we ignore the mass of this wire, we consider only the mass and the weight of this ball. This is called a simple pendulum. Simple pendulum. Because it's really simple. It's the simplest case of a pendulum. So it is called a simple pendulum. So we can consider the torque, the net torque on this ball when it's at an angle theta relative to its equilibrium position. and the net torque should be equal to mgl sine theta. So why here is a minus sign? Because when you increase this angle, like we put it here, the torque is going to make it go back to its position. So when you increase the angle, the torque tends to decrease that angle and make it go back to O prime here. So that's why here's a minus sign, because the direction of the torque is always in the opposite direction of the, like what we said, the angle, right? When you increase the angle, the force will the torque tends to decrease it, right? So you want to, if you put it here, the torque tends to decrease it. So that's why here's a minus sign. So mgl sine theta. That's the torque on this ball relative to the point O. So if the angle is very small, like less than 5 degrees, it's convenient to use this approximation. Sine theta is approximately equal to theta. So we can transform this equation to this. So that's the torque on this. There is something similar between this equation and the equation in previous slides, the force on spring. So let's say here. So the spring, the force is equal to minus kx. So x is the displacement or the position of this object, of this ball, and here angle theta can also represent the position of this ball. And for given pendulum, this part mgl is a constant, just like a k, a positive constant. So that means the torque is equal to minus some constant and a position. It's very similar to this. The force minus some constant position. So, torque minus some constant position. So if we compare these two equations, we can find that they are similar to each other. Okay, so about the spring, so let's calculate this first. So when a family of 4 of the total mass of 200 kilograms step into their car with 1,200, like 1,200 kilogram car, the car spring compress 3 centimeters. So what is the spring constant of the car spring, assuming they act as a single spring? So you know that if you have that experience, when you enter a car, you can feel that the height of the car like changes, right? So something changes, like you just like you are compressing something. So what you are compressing is just like a spring in that car. Actually, there's something works like a spring, like as a single spring in that car. So when you step into that car, you will compress it. You can actually feel that. So in this example, when they step into the car spring compresses 3 centimeters. So we can calculate the spring constant, because according to, so in this case, we only need to consider the magnitude. So the magnitude, originally the equation should be F equal to minus Kx. But now when you consider only the magnitude, so the magnitude is equal to Kx. So that's why K is equal to the force over the change in distance, change in the length of the spring. So the added force is the weight due to the mass, 200 kilogram is about 1,960 Newton. That's the weight of this of the family, right? And the length of spring changes 3 centimeters, which is also equal to 3 times 10 to minus 2 meters. So we can find the spring constant. So this equation usually is called Hooke's law. F equal to minus Kx is usually called Hooke's law. Okay, so how far will the car lower if loaded with 3 kilogram rather than 300 rather than 200? So if it's 300, the force is 300 kilogram times 10 times 9.8 meters per second square. So that's the weight of this load. And K is still the same spring constant. So for a spring, usually the spring constant is the same if when the change of the length is not so large. So this case the same as this one. So we can substitute this one into here and find that's 4.5 centimeters. But the heavier it loaded, the lower the car. So that's why you can feel it if someone heavy, very fat, go step into your car, you can feel that your car get lower significantly, right? So that's that might be a daily experience. So there are many kinds of oscillations, and the simplest oscillation is called simple harmonic motion or simple harmonic oscillation. So simple harmonic motion, or for short SHM, is the simplest one. So if an object moves with simple harmonic motion, whenever its force is proportional to its position and is oppositely directed to the displacement from the equilibrium. So this is described by like the words, but if you use a equation, that means F is equal to minus Kx, or the torque is equal to minus something like constant K theta. So that's also how we determine whether the motion of an object is simple harmonic motion or not. Just like it's a definition according to the force on it. So if the force on this object, is proportional to its position and is oppositely directed to its displacement, the motion of this object is simple harmonic motion. Just like a ball on a spring, the motion of that ball should be simple harmonic motion because it satisfies this equation. It satisfies this equation. And the motion of simple pendulum is also a simple harmonic motion. Also simple harmonic because the torque is proportional to the position theta and is in the opposite direction of the theta. Because when you increase the theta, the force tends to decrease it. The torque tends to decrease it. So that's how we determine whether a motion is simple harmonic motion according to the force on it. But this is not the only way to determine whether the motion is a simple harmonic motion or not. There are other ways, just like in the previous chapters, when we describe a motion, we use a function to describe this motion. So that makes us wondering. So if we can determine whether the motion is a simple harmonic motion directly by the motion itself, but because sometimes we do not, maybe you do not know the force on it, you just know at what time where it is. So if we mark the position of this object at different time, and we record this, so whether we can determine if it is a simple harmonic motion according to our test. So that means we need to find out the real position, just like x at different time. This function, we are going to find out this equation is equal to what? What kind of function it is? What kind of equation it is? So this is a problem in mechanics. So Newton's laws can be applied here. So we still start with the simplest case, an object on a spring. That's the simplest case, always be the simplest case. So just like here, a block or a ball, that's the same. The smooth surface and at this position, x is equal to 0. The force is 0. At some position x, the force is in the opposite direction of displacement. So F is equal to minus kx in this case. Okay, so just like this, minus kx. And according to Newton's second law, it should be equal to ma. And also, like a is equal to the second order derivative of the position relative to the time, so which is also equal to x. So minus kx is equal to this. That's Newton's second law. So we can move everything to the same side. That's m second order derivative et squared. It's e plus a x is equal to 0. And then let's make the coefficient here to be 1. That's x. So I'm writing with the mouse. So not that beautiful. A over m x is equal to 0. So maybe in the other courses like calculus, the teacher has told you how to solve this second order differential equation, but we are not going to use the method that you used in mathematics, because that is very complicated, and according to calculus, they will give you a solution, and that solution might be a complex solution. But in physics, like here, x is a displacement or position. It cannot be a complex number, right? It must be real. It must be a real function, but not a complex function. So it should be a real function. So if it is a real function, so in physics, we usually guess the solution. We guess to find out the solution, and then we determine other parameters. We guess to find, we guess something like what kind of function might be the solution of this. So you can see here we take the second order derivative and then equal plus something, still this function, and then equals to 0. To satisfy this equation, x can only be two kinds of functions. One is like e, or something like here is some power like this. And the other kind might be a sine or cosine function. Sine or cosine. If x is equal to some sine or cosine function, that is definitely one solution of this. So maybe it's a something like, it's, for example, x is equal to like sine. So maybe we can make it simpler. We let k over m to be equal to what we call omega square. So we change this part into omega square. Change this part into omega square. So one solution of this function is x is equal to sine omega t. It should be one solution to this. Because when you submit this sine omega, take first derivative is omega cosine, omega cosine or omega t. And then another time that's minus omega square sine omega t. Now, and they can cancel this part. So sine omega t is definitely one solution of this, but it's not a general solution, it's a special solution. So maybe we can plus some constant to this. That will not affect this. This is still a solution of this. And we can put another coefficient here. It's still a solution of this one. No matter you use sine or cosine, they can be one solution of this. And here A or omega, we already know omega. A and phi are the parameters that we are going to determine. So that's how we solve this equation. We do not solve this equation, we just guess. We try to find some function can satisfy this equation and make it to be general. Okay, so let's remove all this. Maybe it's time to take a rest. Yes, it's time to take a rest. So let's take a rest and we will go on. We will go on after 5 minutes. And okay, and I will try to mark the attendance for the second time. Sorry, not this one. Not this.
Teacher, can you mark me present for the first time? Teacher, hello, teacher.
Okay. Yeah, go on. So, uh, I would just tell that the School of International Education, they will update the list released recently. So because they just received a list of rejection, so they will update list recently. So don't worry about that. They will update it recently. So let's go on. So uh, we just said, okay, the force act on this object is equal to minus kx. And according to Newton's second law, it should be equal to d squared x over dt squared. The mass times the acceleration. And then we can transform this when move minus kx to the other side and change the coefficient before second order derivative be 1. So we can build a differential equation for this simple harmonic motion. And to solve this equation, as we said, we can just guess. Find that the solution should be a cosine or sine for function. So just like this is a general solution. If you are going to find the special solution, you need to consider the initial condition so that we can solve x and phi. Here, omega is equal to the square root of k over n. Omega is equal to the square root of k over n. So here, the coefficient, the parameter like a and phi, need to be determined by initial condition. We will introduce how to solve a and phi later. So that's the particle in simple harmonic motion. So the solution is based on the spring, something is connected to a spring. But this process or this method is very general. So for the pendulum, we can use the similar method and get a similar function, which is also a cosine or sine function. So this result tells us that if to describe this simple harmonic motion, we can use the force on it representation in dynamics. If the force on it can be, you can use a function like minus kx, describe it, just like it's proportional to the position in opposite direction. That's a simple harmonic motion. So that's the representation in dynamics, like we use when you know the force on it. But sometimes we did not know the force on it. We just know the position. If this position is a sine position or is the function of position is a sine or cosine function, that is also a simple harmonic motion. So if you want to determine whether it is a simple harmonic motion, there are two methods. One, you can analyze the force on it. If the force on it or torque on it satisfy this equation, that just like is proportional to the position, but in opposite direction. Okay, that's a simple harmonic motion. But if you do not know the force, but you know the position, you know that the position of the object can be described by a sine or cosine function, that is also a simple harmonic motion. So sometimes we call this function the equation for simple harmonic motion. Oh, SHM, simple harmonic motion. So the function or equation for simple harmonic motion is a sine or cosine function. Here, x is the position or displacement, and a is the amplitude. So a for amplitude. Omega, we call it angular frequency. It is proportional to frequency. And here, phi, we call it initial phase or phase angle. So we can use a xt diagram to describe this motion. It describes the simple harmonic motion. So we are going to discuss the parameters like here, A, omega, and phi, these three parameters. So in this part, there may be many equations, and we need to do many calculations to get familiar with how to determine the function or the equation for simple harmonic motion. So A here is called amplitude, and in Chinese we call it 振幅. So 振幅, 振 means oscillation, 幅 means amplitude. That means the amplitude of an oscillation. So 振 means oscillation. So oscillation in Chinese is called 振动, oscillation. 幅 means magnitude or the amplitude. So here 振幅 together is the amplitude of the oscillation. So it means the maximum of the displacement relative to the equilibrium. Just if we describe it with a xt diagram, you can see the height of the top is the amplitude. So this is the amplitude. Sometimes we can use a xt diagram to directly find out the amplitude of a simple harmonic motion. So, sorry. So this part, there might be something wrong. Oh, this part. So the amplitude depends on, well, on the initial condition. So, for example, just like the simplest case is a ball attached to a spring. So you pull it with a distance and then release it. It will move back and forth. How far you pull it, and it will determine how far it can travel. So that's why it depends on the initial condition. It depends on initially how far you pull it and then release. So that's why we say the amplitude 振幅 depends only on the initial condition. So for oscillations with different amplitude, you can see the height of the curve is different. The difference is in vertical direction on this diagram. So amplitude is connected to the energy. Actually, it's connected to the energy of the oscillation, and so we will discuss this later. And it actually reflects how strong the oscillation is. The amplitude can tell us how strong the oscillation is. So actually, we can feel this. So if the amplitude is very large, we can feel that the oscillation must be very strong so that it can travel that fast, that far away. So amplitude reflects how strong the oscillation is. And then the period. So period in Chinese, we call it 周期. So 周期 is the period. So this word just so 周期 it come out from like circular motion, or just like we have already learned 周期 in like period in circular motion, right? So in Chinese, 周 means a cycle. A cycle. 期 means time. So together, 周期 period means the time required for one complete cycle. 周 means a complete cycle. 期 means time. So together, it means the time required for a complete cycle. That's period. So on a xt diagram, the distance between two identical points is the period. Like this one between this top and this top, that's the period. And from 12 to 12 to ultra crest to crest, that's also a period. Like from here to here, it's also one period. And also from here to here, it's one period. But from here to here, it's just half a period. So because it's half a cycle, a complete cycle. This is a complete cycle. This is a complete cycle. And this is a complete cycle. But from here to here, only half a cycle. So that's half t. So the distance between these two is half t. Another parameter is called frequency. In Chinese, we call it 频率, 频率, frequency. It means the number of complete cycles per second, or how many times it oscillates in 1 second. How many times it oscillates in 1 second. So that's 频率. So if we compare these two, we can find out the relation between these two. The relation between these two is if the frequency is equal to 1 over the period. That's the relation between these. So frequency or period tell us how fast it oscillates. Tell us how fast it oscillates. So why? Because when you compare these two curves, you can see the red one with greater period, but a smaller frequency, and the other one with greater frequency but smaller period. So you can because the slope on xt diagram reflects the speed. So you can see the slope of this one is greater than this one. So that means the speed of this particle which is oscillated, is faster than this one. So that means greater frequency means faster speed. Greater frequency means faster speed. If it oscillates with a greater speed, that means it must have a large frequency, must have a greater frequency. Greater frequency means it oscillates faster. And as we said, the omega is proportional to frequency. So then we are going to find out the relation between these three parameters. So it's easy to find out the relation between T and F because F is equal to 1 over T. But the relation between omega and F is not that obvious. So there is a simple method to help us to find out it. Because after each cycle, this system recovers its original states, which means after a period, the particle will go back to its original position, right? After one period, it will go back to its original position. So no matter we use sine or cosine here, this is the position at time t. It should be equal to the position after one period t. So that means after one period, if these two are equal to, this one is equal to the other, that means the angle, this part, difference between this and this must be 2 pi, so that it can be equal to each other. So, and this gives us the result, omega is equal to 2 pi over t. So that means it's also equal to 2 pi f. It's also equal to 2 pi f. That means the omega, the angular frequency, is proportional to the frequency. It's proportional to the frequency. So this is very close to the equations that we used in circular motion, right? In circular motion, omega is the angular speed. So angular speed is equal to 2 pi over the period. That's exactly the same. So, and it's not by, it's not the same. So it's the same, not only this the same. In later, we will find that actually the circular motion has some internal connection to simple harmonic motion. And usually the frequency and the period depends on the system itself. So usually we call it lateral frequency or intrinsic frequency. So intrinsic frequency or lateral frequency. That means it's a part of the nature of the system itself. For example, for the particle on a spring is equal to this. K is the spring constant. M is the mass. They are all the characters of the system. So it will not be affected by the initial condition, like how far if you pour it, it will not change the frequency or the period of the system. Okay, so let's come to the other one. So it's a sine or cosine function. So A cosine omega t plus phi or sine the same. So this part, omega t plus phi together, this angle is called phase. Phase characterizes the motion at time t. So why? Because this angle, this phase, can determine the sign and value of x. So x is equal to a cosine phi, right? So it can determine the value and sign of this. And also it can help us determine the sign of velocity. And in different when it for different value of this phi, actually the value, the sign of x and v should be different. So from when it changes from 0 to 2 pi, there is no same state. Because maybe the value of xv can be the same, but the sign may not be the same for all the different values of phi. So when the phase changes within 0 to 2 pi, the oscillator has no same motional state. And when the phase difference is n times, the whole times of 2 pi, the particles are in same motion. So because when you add an angle to this sine or cosine function by 2 pi or 4 pi, then will not change the value, right? But if the change is within 0 to 2 pi, no state. You can see here, from 0 to 2 pi, no same state. Maybe you can see here, this one and this point and this point, both are 0, but the speed is not the same, because you can see and here the speed is negative because the slope is negative, and here the speed is positive because the slope is positive. The sign of the speed can be different at these two positions, and at all the other positions, no same, there cannot be the same state from 0 to 2 pi, but you can see after 2 n pi, they should be the same. So this table can tell us the difference of the signs in different regions. But we focus more on, usually we focus more on the phase when t is equal to 0. So when t is equal to 0, the phase is called phase angle or initial phase. Initial phase and phase angle means phase at t is equal to 0. And phase angle describes how long before or after the maximum displacement is reached. So you can see in this picture, here is the maximum. So how long it takes to reach the maximum from here to here, it's proportional to phi. So it's proportional to phi. So it reflects how long it takes to reach the next maximum. You can describe this. And for oscillations with different initial position, you can see just like from this one to this one, we just like move this horizontal. And we can define phase difference to be the difference between the phase of two oscillations, of two simple harmonic motion. It's two special cases. If the phase difference is equal to 2 and pi n is an integer. So this is called in phase. The in phase means the same steps. They reach the top at the same position. They reach 0 at the same position. They positive at the same position. They negative at the same time. So that is called in phase. You can see Actually, these two, you can treat them as the same oscillation, right? They are in steps. They will always get same step. But if the phase difference is equal to 2f plus 1 pi n is also an integer, this is called reverse phase or antiphase because you can see these two oscillation. One is they reach the maximum at the same time, they reach zero at the same time, but they are always have the same opposite sign. One is positive and the other must be negative. This is called antiphase. Okay, so we have introduced the definition of all these parameters. So now the first example, the position of here SHO means simple. Harmonic, O means oscillation. O means oscillation. The position of a simple harmonic oscillation is given by this equation. Try to determine the amplitude, frequency, phase, and period and initial phase of this simple harmonic oscillation. So maybe you can try to determine this by yourself first, and then I will help you to do this later. So try to calculate it by yourself first. It's the simplest. This is the simplest question in this part. When we give you a function of simple harmonic motion, you need to find out the amplitude, frequency, period, and the initial phase. Try to calculate the Bell-cell first. Okay, so let's do it together. So how to determine all this? We just compare it with the standard form of a function for simple harmonic motion. X is equal to A cosine omega t plus phi. So if we compare it with the standard form, you can find that this part is the amplitude. So A is equal to 0.80 meters. And omega is equal to pi radians per second. and phi is equal to minus 0.25 radians. So remember that here angle is measured in radians. So how we determine this? We compare it with the standard form. So when we compare it with standard form, we find that A is equal to 0.80 meters. And the initial phase actually should be minus 0.25 radian. And the angular frequency omega is equal to pi radians per second. Okay, we get this. We have already got this. So the next step, we are going to find out the frequency and the period. We use the relation between frequency and period and this. So omega is equal to 2 pi f and also equal to 2 pi over t. So if we know omega, we know t is equal to 2 pi over omega, which is equal to, 2 pi over pi, that's 2 seconds. And the frequency is equal to 1 over t, which is equal to 0.5 hertz. So that's how we solve this kind of problems. We compare it with first step. Erase all this. So period 2 seconds. So we can first step, we compare it to the standard form. So we can determine amplitude and initial phase and angular frequency. So amplitude, initial phase, angular frequency. If we compare it to the standard form, and then we use the relation between frequency and angular frequency and the period, we can determine other parameters. That's how we determine all the parameters when we know the function of the oscillation. So, okay, maybe we can stop here today. So we will go on this part of on Thursday. Okay. So that's all for today. See you next time.
See you.